All right. All right. So last time we talked about infrared divergences in QED, and today we'll continue on with QCD. But QCD is much more complicated. So rather than making precise calculations in QCD, we'll use a combination of some new QED calculations, and sketching to understand the nature of these divergences. All right, so we will first start with a better understanding of the infrared divergences in QED and of how they exponentiate and factorize. So one observation that we made before was that if I write the dimension as d equal 4 minus 2 epsilon, epsilon positive regularizes the UV divergences, whereas epsilon negative regularizes infrared divergences. We also saw that in order to map, calculation in photon mass regularization to dimensional regularization, we have to basically drop the 1 over epsilon, the poles in epsilon, from dimensional regularization, and map the photon mass to the dimensional transmutation parameter mu. However, the map is rather more precise. So precisely, the map corresponds to this transformation. So between log of mu photon squared over mass squared to gamma of epsilon 4 pi mu squared over m squared to the epsilon. So let's expand this right-hand side. So it's gamma of epsilon is gamma 1 plus epsilon over epsilon, and 4 pi mu squared over m squared is starts at 1, and then 1 plus epsilon log 4 pi mu squared over m squared. And then gamma of 1 plus epsilon is 1 plus epsilon 1 minus epsilon times gamma, the Euler constant. So then expanding, I get the 1 over epsilon pole, and then minus mu plus log 4 pi mu squared over m squared, which includes also log 4 pi and log mu squared over m squared. So indeed, log mu photon squared over m squared is mapped to log mu squared over m squared as a divergence in mu photon or mu going to 0, also dropping 1 over epsilon. But as you see, there's also in the map, we can also include this finite piece minus gamma plus log 4 pi. So this map can be just obtained from the two calculations that we did before. So we expanded, we concentrated on in the mu going to 0 terms, but we can we can check that this map really maps the one loop calculation in both regularizations. So part of the reason why I said epsilon positive regularizes UV divergences and epsilon negative IR divergences was the calculation of integrals of this type, integral ddq over q squared to some n, and in particular n equal to 2 is the relevant thing. And then, you know, this integral will be from some IR cutoff to some UV cutoff, and then we see this fact. But we can generalize this. We can note, moreover, that we have gamma of d over 2 over pi over d over 2 times I. And then, moreover, write in a given the fact that UV and IR divergences must be regularized in different way, we can write this. So note that this particular integral in dimensional regularization is actually 0, right? So, but to write it in a way that emphasizes the fact that we said before, we write this in a way that we will think of the integral at the upper end over dimensions that are d minus 4 to epsilon, and the integral at the lower end over some d prime, which is d4 plus equal to 4 plus 2 epsilon or minus 2 epsilon prime. So in this case, the integral itself can be written in this way, with a dimension d and a dimension d prime. And then, so in this way, we regularize both divergences, and at the end of the calculation, we just have to put d equal to d prime. So in particular, also the vertex that the QED vertex that we calculated last time still had UV divergences. Just those were the things that we dealt with in previous lectures at the beginning of the course. And those were dimensionally regularized with D, whereas the IR divergences would be regularized with D prime, or equivalently with a mass through this mapping that I described here. So then the vertex in dimensional regularization has this form given here. And here there's some more function that one can also calculate of this variable, so really of m over q. But the rest is well defined, and we note that, well, we have the same function. So this is equal to well, this and this, sorry, equal to this and this. Oh, this and this, except I have to map this this times this into this, which is the map we described here. But then I also have this so this would be the UV, the actual UV divergence in dimensional regularization of the vertex, which is mass regularized in the IR, whereas in here I would have this new IR divergence in epsilon, in mass regularization, but I would still have this UV divergence, so the leading 1 over epsilon object. All right. Okay, so this is the example of QED. As I said, for QCD, things are a bit more complicated. But for the vertex itself, so if I consider the same Feynman diagram, this with a photon here, the same Feynman diagram like this, but just instead of electrons here, put quarks, and instead of photons here and here, put gluons. And then, of course, the coupling would be different. The coupling would be G strong instead of E, or equivalently. So I can define alpha strong being G squared over 4 pi in the same way I described alpha equal to E squared over 4 pi. But we also have to remember that there are gauge indices also, in particular gauge indices in this loop. And that will give us a factor of CF, C in the Casimirian, the representation, fundamental representation of the quarks. All right, so the calculation would be, in this case, would be just the same. So in the case of QCD, we don't need to do anything. So we can still infer the same map between photon now it's gluon mass regularization and dimensional regularization, and also the same comment about the UV and IR divergences. Next, let's understand a little bit the issue of the exponentiation of IR divergences and of factorization. And in order to compare with QCD, which is more complicated, we'll also do it in a more formal way. So the physical calculation of the vertex would be with some external U bar of P2 to the left and U of P1 to the right. And then one can rewrite this as the classical vertex E gamma mu times something that some new function that I'll call alpha gamma, that depends in dimensional regularization on epsilon and on the ratio of the photon momentum q squared over the electron mass m squared. And also mu to the epsilon, just in order to fix dimensions in dimensional regularization. So then alpha gamma it can be expressed in this way. So really, from the calculation we had before, you can look it up, and you can show that it can be written in this way. Now, the point about writing it in this way is that now in these denominators, we have, since we're doing, well, I mean, sorry, so the part we're interested in is the infrared diversion part, where I write here. So K, the momentum in the loop, will be very small, right? So there's 1 over k squared here, and the divergence comes when, because in the denominator, the thing that dominates is this 2p1k dot k, and in this one, 2p dot k, 2p2 dot k. Either way, it's 1 over k, and then it's squared. So 1 over k squared times 1 over k squared, 1 over k fourth, integrated over d4k. That gives the log divergence. But of course, this amounts to neglecting this contribution, k squared in the denominator, which is reasonable for infrared divergence. However, the point is this approximation is known as, well, it's a leading divergence approximation, but it's also called an Iconal approximation because of its relation. So really, the Iconal approximation is the approximation in quantum mechanics where you consider light rays, basically, the approximation of a wave function where you consider only light rays. So that amounts to an approximation on momentum, and that in turn relates to this approximation that k squared is less than 2p1k and 2p2k. Now, we've seen last time that the infrared divergence first exponentiate and second factorize into a so-called hard part that contains large momenta, specifically contains, so the vertex we're interested in has, well, finite or even large momenta for the external lines, but the loop, in the loop, or correspondingly when we try to cancel it, in the momenta of the emitted photons, we have soft or low energy, low momentum particles. So again, then the vertex factorizes into a hard part, and then a soft part that is exponentiated. Moreover, it's a scalar factor. I mean, that's what exponentiated means. Exponent of a number. So, and that number is this approximation that we've derived here, the Iconal approximation, the leading divergent part. So gamma mu is written as this exponent of alpha gamma Iconal times the gamma mu hard, the part of the vertex that depends only on the large momenta. However, the vertex itself, and then according to the factorization property, gamma mu hard itself still has a UV divergence. Gamma mu is hard, so contains the large energies. Then we can also factorize in a different way. We can factorize gamma mu as a finite part, gamma mu finite, completely finite, times exponent of an alpha gamma that contains both the Iconal part of the IR divergence and the UV divergence. But therefore, according to our previous discussion, it will be depending on the epsilon of dimensional regularization and on the ratio of momenta. So specifically, we've defined that it should depend on q squared over m squared. And usually one defines q squared as minus capital M squared. So I say gamma of epsilon and capital M squared over m squared, just to show that there's a ratio of mass scales involved. And then the final part is obtained by comparing these two. So is this hard part of the vertex times the Iconal part of the IR divergence minus the minus this this part gamma that contains all of the divergences. All right. But really, if we're talking about QCD, the issue that we're interested in is cross sections, things that we can actually measure. So if we want to map this calculation to QCD, we should consider a cross section. And we already see that that QCD is asymptotically free. So asymptotic freedom meant that experiments at high energies are perturbative, but that means that alpha strong goes weaker with the increasing momentum, but then goes stronger with the increasing momentum. So in principle, we would think that there's a problem that at low momenta cross section might diverge or something, but in fact they are infrared safe, meaning that they are finite for low momenta. And specifically, this because of simplicity, and because of A, simplicity, B, we want to compare with a QED calculation, and C, because it's experimentally relevant, we consider the process of E plus E minus, electron positron, going to hadrons. And we'll see that from this we will need to define the beta function, and from it, in turn, define the running of the strong coupling constant. All right. So one way to describe this infrared safety of the cross section is to say that the cross section depends on the coupling, depends on I mean, so in dimensional regularization, let's say, or well, in any kind of regularization, we would introduce a mass scale mu. But specifically here in dimensional regularization, I would write that it depends on the ratio of the electron mass to the mass scale mu, and also on the on this q squared over mu squared, or equivalently, the way we said here, on the ratio of the capital M mass and the mass scale. But we should, so infrared safety means that we have something that is infrared safe, something that is finite, and then it's finite when the mass of the, well, quark here, before it was electron, is much smaller than this momentum of quark or gluon. And we can expand in this m squared over q squared. Moreover, this is a actually free theory, so we know that the renormalized mass, in the case that we take this mass scale, arbitrary mass scale mu to infinity, should go to 0. Then that means this expansion makes sense. Because q going to 0, q going to infinity, or mu going to infinity is a possibility. We can think of, we can choose, if we want. So remember, we can choose the arbitrary mass mu to be equal to q, the momentum, the total momentum of the process, and then also from this we also see that the high energy, meaning q going to infinity, and 0 mass, meaning m going to 0, limits are also equivalent. As we said, we will define the running coupling constant through the cross section, since that is what one does. So one does experiments, one measures cross sections, and from them one infers the running of the coupling constant. So we will do that as well to see how that works. But to reach that, we will try to describe better how the these cross-section work. So, so what cross-sections are we interested in? Well, as I said, we're interested in the process of physical process, which was so one of the cleanest experiments, and one in particular that was done at LEP, one of the first experiments at CERN. Well, not one of the first, but well, one of the first experiments for the high energy regime, is to collide electrons with positrons because they're point-like, and so it really probes what happens after the collision. So after the collision, you create well, you create a photon, and the photon itself can decay into well, here will be so in QED we would say will decay also into electron positron, but in so that's one possibility, certainly. But another possibility that is relevant for what we're doing is to consider the decay into quark-antiquark. And then, since the quark-antiquarks cannot be, they are not free in the infrared, they cannot exist by themselves, then this will go into hadrons. So this process of quark-antiquark going to hadrons, or hadronization, is complicated, is something that we cannot describe in perturbation theory. One usually uses a combination of some lattice and some experiments and so on to define how that works. But one can parameterize it. And to understand this, let's consider this process. Let's consider this process in the following way. So let's consider first just going to so when we just have Q bar in the final state. The way to obtain the cross section, as you know, a total cross section, I should say, for all of that. Oh, okay. No, sorry. The way to obtain this cross section, going to Q bar, would be to consider the amplitude for electron, positron going to gluon, going to Q bar loop, then going to then mirror image going to photon, going to electron, positron, and then cut this loop. Remember, the cutting meant that we on the mass shell, we make them physical, and that amounts then, or equivalently, through the optical theorem, the cross section, well, through a restriction of the optical theorem, the cross section is the total cross section was equal to the discontinuity in the imaginary part. amplitude, but a simple way to think about the cross-section itself. The cross-section is proportional to an amplitude modulus squared, that is m star. And if you put m, so this amplitude m, with m star, which basically corresponds to the mirror image, and you put them together, you arrive at this one loop amplitude with a cut, meaning that the intermediate line, the QQ bar line, are on shell. So we will not reproduce the calculation, but I mean, it's not complicated, but the result of this is that the differential cross-section of d sigma with d cos theta, relativistically this corresponded to d sigma dt, the Mandelstam parameter t, but physically it's d sigma with respect to d cos theta, where theta is the angle between the colliding particles. Sorry, between the initial and final particles, is equal to, it has to be proportional to alpha squared. Then there's this n colors pi over 2. There's 1 over s, so it grows, it decays like 1 over s at large colliding energy. But then the interesting thing for us is that there's this sum over quarks, the sum over flavors of quarks, f, the electric charge squared of this quarks, and then 1 plus cos squared theta. If we integrate over cos theta from -1 to 1, so so this is the d sigma d cos theta, then you integrate with cos theta, you get you get a numerical factor, 8 over 3, I guess. And so there's a numerical factor that just modifies this prefactor, but then I'm left with sum over flavors of quarks, q squared, electric charge squared of the flavors. Why this is important? Because experimentally one can define and measure very precisely the ratio of the total cross-section of E plus, E minus going to hadrons to the total cross-section of E plus, E minus going to some leptons. One chooses usually mu plus, mu minus, just because if you see E plus, E minus, you have a different, you have two Feynman diagrams, so that's not relevant, but it has to be some other lepton, and the next lepton that's available is mu. And so the ratio of these two things then is just n. I mean, that's the number of colors times this factor, sum of the flavors of quarks, qf squared. So in this, so R is equal to this, considering this process. So considering that for our E plus E minus going to QQ bar process, we just consider this tree diagram, right? And then this thing is just cross-section for E plus E minus going to QQ bar. Remember that then we have this hadronization business that QQ bar goes to hadrons. So this is the value at 3 level. So when in perturbation theory in alpha strong in the 0th order. But we can measure this very precisely, and this is actually why this is relevant, because this is one of the most stringent tests of QCD. And it shows that, well, it shows very precisely that there are 3 colors, and it shows it. Sorry, it constrains this combination. But since we know that there are 3 colors, and we have seen the number of quarks and their charges, we know that to calculate this, and we know therefore that there is no other quark or gluon, because this we already obtained this number. However, what we're interested in, so this was the result at 3 level, but we're interested in corrections to this. So this is 3 level plus correction, plus 1 loop, plus 2 loop, plus 3 loop, and so on, right, in alpha strong. So then what we would do is, you would consider the process with E plus E minus going to QQ bar with 1 loop somewhere, right? Let's say I add another loop here, right? And then in the cross section, I would write cross section. Remember, is M star, and this is M, and this is M star. So this would correspond to a higher number of loops in the cross section. Well, anyway, so the one loop, well, there will still be a 1 loop contribution where I just in this MM star I consider 3 part here and let's say 1 loop part here. That would be a 1 loop correction to this result. Anyway, so the point is that when we consider adding these loops, then so when we consider adding these loops, one will obtain a result that can be parameterized in a certain way. So I guess in well, you can find in some other book, you can find the details of the corresponding 1 loop calculation. There are many Feynman diagrams, and it's difficult calculation, but it doesn't matter. What we want to understand is the structure of the result, and therefore the structure of the general result, not only 1 loop, but at all loops. So, all right, so what really we're interested in, we said, is the total cross-section for E plus E minus going to hadrons. But here we've just considered E plus E minus going to QQ bar. Then QQ bar, as I said, hadronized means creates a number of hadrons. And well, it could even create say, could create another other particle. From QQ bar, we can get to, well, we can create a gluon, for instance. I cannot write, but we could create a gluon, and then a gluon itself can create something else, some QQ bar, or even just the gluon themselves, together with the QQ bar, can create 3 jets, which can correspond to at least three hadrons. Anyway, so there's a bunch of hadrons coming from QQ bar. Now, when we look at the cross section, as I said, is comes from MM star. So I write this diagram M for what we want, and then M star, which is the time reversed 1, and when we glue them together, we get this cut diagram. But what does this cut diagram do now? So if in the end here we have hadrons, then we have a cut hadron with where what we cut, we have a cut diagram where what we cut are intermediate hadrons, right? So in this cut diagram, I have E plus, E minus going to photon, going to QQ bar, going to hadrons, and then going back to QQ bar, photon, and E plus, E minus. So there's so we have a sum over intermediate hadrons. So then let's try to understand the parameterization of the final result. As I said, the 1 loop, 2 loop, and so on are complicated already because of QCD. There are many diagrams. It's not worth doing this calculation at this level. But let's just understand the structure of the thing. Well, so what is it supposed to be? Well, we start. So first of all, we have to what we have here is an electromagnetic current that couples to a photon, right? So we have an electromagnetic current. Now, initially, so in this cut diagram, to the left, we have vacuum in terms of hadron. There are no hadrons. But to the right, sorry, to the left of the cut, so to the right of this M diagram, I have hadron states that I'll call these states N. So there's a vacuum here, there's an electromagnetic current, and there's a state N for hadrons. There's a ket, N for hadrons. Then I have M star, so there's a bra for N for hadrons, electromagnetic current, and then to the right I have 0, so the vacuum state in terms of hadron. So I have this combination. I described this combination here: 0 electromagnetic current, N electromagnetic current, 0. And the electromagnetic current has an index mu that will couple to the photon, right? So yeah, then there's also yeah, and of course there's a sum over all of these states n of hadrons. That was the point, that we have intermediate states here, but we sum over all the possible intermediate states in the cut in order to obtain the total cross section. And then we see that if I define the momentum q of the photon, so this is, let's say, q, then q must be equal to, by momentum conservation of the amplitude m. Remember, this is to the right here. I mean, in the cut, this is on shell. Q must be equal to the total momentum of the hadron state n that we cut here. So I must have also delta of Pn, P of the state n, minus Q. I also have to have, well, we're doing dimensional regularization, so we'll have this thing. There's E squared because, well, I have E here and E here for the coupling, and moment in dimensional regularization, I have mu to the power 2 epsilon. All of these together forms this function that I called it h mu nu of q squared, right? But then for the total cross section, I have mm star, so I have this factor squared. So I put one factor in, then I have another factor outside. Then what? I have 1 over q squared propagator here, 1 over q squared propagator here. So 1 over q squared one over q squared, 1 over q squared. Yeah, it should be 1 over q squared squared. And then I have this, and then this h mu nu has to contract with some with something that that has no dimensions but has indices, Lorentz indices mu nu, right? And so the combination that one obtains is this one. Also, because we have to respect gauge invariance, so K1, K2 being these momenta, we have to respect gauge invariance, and the corresponding extra factor is this one divided by q squared. So all in all, we have this factor q to q squared cubed. All right. Then also the same gauge invariance now applied to the factor h mu nu that came from this part. This was h mu nu of, depending on the photon momentum q, but contracting gauge invariance means contracting with gauge invariance of this means contracting it with q mu or q nu should give 0. So then that means this structure, Lorentz structure, has to be q mu q nu minus q squared g mu nu times a scalar function h. So this is the general structure that one has for the total cross section, okay, at all orders. Now, so there's a long calculation for the total cross section that's similar to the ones done in QED, where, as I said, we can add a loop to the amplitude m. So I can add, so there are very many diagrams, but I can add a loop here to m, and correspondingly also to m star. And calculate this two-loop result, but that will be infrared divergence. And then, in order to have a finite total cross section, we remember that we can also emit weak, soft gluons or photons from these fermion lines, either from the initial ones or from the final ones. So then I can calculate this result, g mu nu, h mu nu. The real part means the part that corresponds to emitted gluons. So the part where here I just put some extra emitted gluons, either from here or from here, correspondingly in m star as well. So the real part is given here, and the virtual part means actually adding a loop to m and also to m star. So the result then of this two-loop H is one loop H is 1 over epsilon squared. As I said, for gluons, I have the most divergent part is 1 over epsilon to the 2L, the 2 times number of loops. So I have this combination 1 over epsilon squared, some 1 over epsilon on some finite part. And then the important part is that, again, I get this QF squared, the number of the electric charge squared of the flavor of quarks, and N, but also now I also get alpha strong times C2F, the Casimir in the fermion representation. We also see, so this comes with plus, this comes with minus. We also see that these are both infrared divergent, but when we add them up, as I said, that's the point, that the diagrams with loops and the diagrams with emitted photons or gluons should cancel their infrared divergence and just leave a finite result. So indeed, these divergences cancel. Moreover, some finite part also cancel as well, but then we're left with some finite part, and it's proportional, as I said, with alpha strong times C2 C2F. So alpha so there's an alpha here that came from this E squared, and there was another alpha outside. So that gave the alpha squared from the tree result. So I put here the tree result, like a correction to the tree result. So the tree result would be this, but then I have 1 plus this combination. Okay. So 1 plus alpha strong over pi 3/4 C2F. Okay. Now, at this one loop level in the amplitude, we see that this correction to the R factor, to this R factor, this one loop correction is independent on the renormalization scheme and on mu. It's also independent on the dimensional transmutation scale mu. However, that's only at one loop. At the next order, I will get something non-trivial. So I will get, again, alpha strong over pi now squared, but then I will get a function of q squared over mu squared, so a function that something that depends on mu, and moreover is scheme dependent. Renormalization scheme dependent. But now we remember that the total cross-section is a physical object. It's something that we actually measure. So it cannot be dependent on either the renormalization scheme or the arbitrary dimensional transmutation scale mu, right? So the only possibility then is that there is a combined dependence. So both alpha strong, so there's an alpha strong here in the corrections. So both alpha strong and this function must depend on renormalization scheme and on mu in such a way that their combination in sigma total cancels. So there's only the dependence, their dependence in sigma total cancels. Right. So one formal way of saying it is that the total dependence, so sigma total depends on q squared, that we knew, depends on mu squared, apparently, and alpha strong also apparently depends on mu squared. But then the total, so the total dependence, so mu d mu, I cannot say, d mu here, which is equal to mu partial d mu plus beta of g, which, as you remember, is mu d mu of g times partial ddg of sigma total is 0. All right? So that's the formal way of saying it. And then from this we derive, we infer alpha the dependence of alpha strong with the scale mu as being related to this function a2, this function a of q squared over mu squared. There's an a priori independent. So this is a definition. So this is the definition that we use experimentally, right? So we calculate this result to whatever order we want, and then note that the sigma total should not depend on mu through this equation, and from it we can plot the dependence of alpha strong with the scale mu. Notice also that, as I said, mu is an arbitrary scale, and one usually can consider the useful choice mu equal to q, the momentum of the photon, the momentum of the intermediate. So the total momentum of the collision E plus E minus is equal to the momentum q of the photon. So I can choose mu equal to q, equal to q, and alpha strong is alpha strong of q squared. Okay? So that's what one does experimentally. But an a priori independent definition of alpha strong is directly from the beta function. So that we will call alpha tilde strong of mu squared. So alpha strong is g squared over 4 pi squared, right? Sorry, g squared, g squared over 4 pi, sorry. And then mu dd mu of alpha strong tilde over pi is 2g tilde beta, which is mu dd mu of g, over 4 pi squared. So now what's g tilde over 2 pi squared beta of g tilde strong. Now and now I define the beta. If you remember from before, we've discussed the general structure of the beta function, and we write it as well, g strong actually. Sorry, here should be g strong. So g strong times alpha strong over 4 pi beta 1 plus alpha strong over 4 pi squared beta 2 plus dot dot dot. Beta 1, beta 2, and so on are numerical coefficients. So we define this beta of g, and then plug in here, and we get this. We define this structure now. So now we have alpha tilde strong over pi squared times beta 1 over 2 plus alpha tilde strong over pi cubed beta 2 over 8 plus and so on, right? So now alpha tilde strong over pi is a polynomial in alpha tilde strong over pi related to integrate this equation from a mu. We can introduce a parameter lambda, sometimes called lambda QCD, the QCD scale parameter. And then we find, so because mu has dimensions, right? So because of this, I have to define alpha strong as a function of mu divided by something. So this is mu over lambda. More specifically, as a function of log mu over lambda. And with a very non-trivial choice defined here of lambda, I mean, this is chosen such that we find a relatively simple form for alpha strong tilde over mu over pi, which is -2 of beta 1 log mu over lambda minus beta 2 over beta 1 cubed log of log mu squared over lambda squared plus beta 1 divided by log squared of mu over lambda plus 1 over log cubed mu squared over lambda squared. So this form now is dependent only on log mu over lambda. The proof of this is left as an exercise. It's just some algebra. All right. Let's continue. Describing factorization and exponentiation of IR divergences in gauge theories. Now, in QED, we've seen how this happened. We started with a statement. Well, where was it? Here. We've said that we have an exponentiation of the IR divergences, and there was a hard part times this iconal this scalar factor containing the Iconal approximation to the leading divergent approximation for IR divergence. And moreover, another way of saying it was that the finite part times IR and UV divergent part. But in QCD, this is considerably more complicated, both to write down the divergent and to factorize it. So to understand how that is done, we need some preliminaries. We need to, I mean, I will not describe this in detail again because that takes too long, but I'll describe just a little flavor of it. Now, to do this, we need must describe the structure of amplitudes in terms of color, in terms of the gauge indices. So we have to define a so-called color basis, CI. The point is, we can consider convince ourselves that for all amplitudes, we only have a few color structure possibles, and their coefficients are amplitudes independent on color, that are sometimes called color ordered. The simplest example for this is for amplitudes with external gluons. Now, of course, in our case, we're interested in amplitudes with external quarks, but as I said, we're just trying to give a flavor for this. So the external, in the case of external gluons, a gluon is something that has an index, an adjoint index A. In the case of QCD, we have 8 possible gluons corresponding to the adjoint 8-dimensional adjoint representation of SU3. The propagated vertices have only delta functions for the fundamental indices I and j. And then that means that these indices I and j are summed over. So that means that we will in doing the Feynman diagrams, what we will obtain will be either traces of the matrices TA, with A being an external gluon index, or the other possibility is to obtain a delta of II. So either, delta ij will correspond to product of TAs, and then finally delta of initial index with final index give the trace. Or there's also the possibility that I have a delta of II of the same index, up and down, which gives just n, the number of colors. So that means that the structures of the color structure, so n is just a factor, but the color structures that are possible are just traces of the TA matrices, the generators of SUN or SU3 in the case of QCD, where A is the index for the external gluon. For example, in the case of 4-point scattering of gluons, so 2 gluons going to 2 gluons, in a theory like QCD, so with SUN, but with SUN, you can just put n equal to 3 at the end, that's fine. But just a theory with just gluons. So SUN means that the trace of the generators TA of SUN is 0. So the only possibility is then, it means trace of TA is 0, and then also you can convince yourself that that also means that trace of 3 TAs is also 0. Sorry, not trace of 3 TAs is not 0, but you have 2-to-2 scattering, so you have 4 adjoint indices. So you have 4 indices, 4 gluon indices, means 4 TAs. And so one possibility would be to have 1 trace and times 3, a trace of 3 TAs, but then trace TA 0, so that is not possible. The next possibility is to have a trace of 2 TAs times trace of another 2 TAs. These are these 3 color structures. Trace TA1, TA2, trace TA3, TA4, and so on, these permutations. And then finally, the possibility is to have 1 single trace of T1, A1, 2, A2, A3, A4, plus the various permutations. But since the trace is also cyclic, I can always put A1 to the first position. So that means that the independent color structure are with the permutations of these next three TAs. So there are 3 permutations means 6. So there are 6 color structures from this trace TA1 with 3 more gluons, and then 3 color structures from these permutations. Picking picking 1 index out of 3. So trace TA1 with another one out of the remaining 3. So I have this 9 possible color structures, 6 single traces, 3 double traces. And so the total amplitude for 4 gluons, 2 gluons going to 2 gluons, will be these color structures times the color ordered amplitudes corresponding to it. So 9, a sum of 9 terms of this type. And then these color structures can be thought of, you can think of it as this element. So you can write this as a ket or a column vector if you want, with 9 components. Moreover, there's actually a reflection symmetry relating the amplitude with this amplitude with 1 to n, with amplitude with the reversed order, n going to 1, with -1 to the n factor. So from this we deduce, so that means I can relate the various objects. So from this I deduce that I can, so from the 6 color structures with a single trace, I can reduce them to 3 by this symmetry property. And the double trace doesn't work, because reverting it does nothing to it. I can you go back to the same. So it's actually a 6 a vector, column vector with 6 components, the ones given here. But anyway, the point is, I write an amplitude expanded in this 6 color structures. And summarizing, I write it as a ket vector, remembering what this means. All right. So now the factorization of the amplitude with so this is for gluon amplitudes. Specifically, I described for you 2 gluons going to 2 gluons, but this particular structure is true more generally for gluons. So the amplitude vector will depend on, will depend on ratio with mu squared, of momenta with mu squared. But what momenta? So is this generalized Mandelstam invariant ki plus kj squared, that I call Sij, so divided by mu squared. Then there's a coupling, the running coupling, which I define in the following way. Well, there's g squared, but actually it turns out that the dependence is actually through the combination g squared times n. And there's some numerical factors that one can put in, and so since G strong depends on mu, I write this dependence as dependence via this combination A of mu squared, and also depends, of course, on epsilon. So there's this factor. So there's this amplitude, and this amplitude now is split into three factors. There's a hard amplitude vector, H vector, H ket. There's a matrix S multiplying it, and a numerical factor, so a number, J, multiplying it as well. J is called the jet function, and it's IR divergent. S is called the soft function, and it's a matrix in color space that multiplies this column vector H, and H is called the hard function. Contains the short distance behavior, and it's infrared finite. Okay, as before. So now both of these J and S are infrared divergent. So you might wonder, why not just absorb J into S? But the point is that J contains all the collinear dynamics. So remember, I said for gluons, for gauge theories, non-abelian gauge theories, we have two kinds of divergences. We have the soft divergence of QED, but we also have the collinear divergence. So now all the collinear divergence of QED goes into this exponential factor, this scalar factor, J. So therefore, J contains at one loop 1 over epsilon squared poles, and generically 1 epsilon 2L at L loops. Then S is the matrix S is defined by the so-called anomalous dimension matrix gamma, which I'll define it shortly, but which is basically a generalization of the anomalous dimension for scalars. So what else is there? Well, there's, in all of them, there's the dependence through the coupling and the epsilon in all of them, right? And now there's a dependence through an arbitrary scale, a new arbitrary scale, capital Q squared. All right. So so all of these three objects now depend on the ratio of these two arbitrary scales, Q squared over mu squared. But the hard part and also the anomalous dimension part, the soft function S, depend also on the ratio of momenta of the hard external momenta, so Sij, divided by this capital Q squared. This capital Q squared is called the factorization scale. It's an arbitrary scale. So as you see, the amplitude does not depend on it. So the only point of Q is that I can factorize the amplitude into these three objects in terms of an arbitrary scale Q, right? So So I can I can write a relation like this for a Q1 and another relation like this for a Q2. But now JS and H are different. Now, I said that S is defined through the anomalous dimension matrix. So this is a matrix relation. So that means that this is a vector. So if I write it in indices in this color structure, I would write AL equal to J, which is just a number, times SLI times HI. H is also a column vector. And then the anomalous dimension matrix, gamma, is defined like this. So the DD log Q, Q being the factorization scale of this S matrix, is minus gamma Lj Sji, right? So this is a generalization of the anomalous dimension of scalar theories, in which we didn't have a matrix, so we just have DD log of a scale equal to minus gamma times this function. We see that there is some similarity with the evolution equations in this factorization business, and we'll see that in the next next lecture that this is not a coincidence. There is actually a connection between factorization and evolution. So, so this is some sort of randomization group equation, and through also this factorization dependence, I can write the this S the soft function matrix as a path order exponential of an integral of the anomalous dimension matrix. So what one does in practice, one calculates the anomalous dimension matrix and then integrates and writes down the soft function, this soft function matrix in this way. So to summarize, so J, the jet function, is just an exponential, just like in QED, e to some Sudakov object, but the Sudakov object was also, remember, expanded in the coupling. So even though it's in the exponent of an exponential, it's still a sum over loops. The same is true here in the soft function. Even though it's a path order exponential of something, this something is still expanded in loops. That is expanded in the coupling, which is in here in A. Okay. At one loop, the coupling A, just just as an example, is written like this. Now, the infrared diversion structure is given by two objects: the cusp anomalous dimension, also known as the Wilson line anomalous dimension or soft anomalous dimension. So the as the name suggests, this anomalous dimension defines soft infrared divergences, which happen to also be anomalous dimensions related to Wilson lines, more specifically to cusps or wedges or angles in the Wilson line. And then there's another anomalous dimension, more collinear anomalous dimension, which characterizes the collinear divergences. And these anomalous dimensions, again, can be expanded in the coupling in A. Now, in QCD, there is an anomalous dimension matrix gamma, which is independent of the two functions, so the cusp anomalous dimension and collinear anomalous dimension. So in QCD, therefore, which is the most important case because it's physical, we have three objects that of interest: the cusp anomalous dimensions, the collinear anomalous dimension, and the anomalous dimension matrix gamma. However, for simplicity's sake, just to give you a flavor of something, because up to now I just said, well, I kind of showed you a formula for S, but I didn't say anything for J. But to say anything for J, I need to restrict myself to a specific gauge theory, very, very special one called N=4 super n mils, where many things can be completed exactly. And I'll not explain to you what this is. It's a supersymmetric theory, but supersymmetric gauge theory, but never mind. I just want to use it to illustrate something, what could be in J. Moreover, so this N=4 super n mils is so simple that in fact it does not have a non-trivial gamma matrix. QCD does. It's a third object of interest, but in N=4 super n mils there are only these two: the cusp anomalous dimension, the soft anomalous dimension, and collinear anomalous dimension. And so in this very simple case, the jet function J, as I said, depends both on collinear and on soft divergences, therefore on both anomalous dimensions. So indeed, in this case, it's an exponent. In the exponent, I have a sum of loops, a sum of an expansion in G squared n in the coupling. I have dependence on this mu squared over q squared, and I also have dependence on the cusp and soft and collinear anomalous dimensions. Moreover, specifically in these coefficients, gamma L and G0L. And also, as I said, each one comes with 1 over epsilon. So the leading divergence here in the exponent is 1 over epsilon squared. So at L loops, I will have 1 over epsilon 2L to the power 2L. All right, but in QCD, in the relevant theory, I also have the anomalous dimension matrix gamma, and things are a little bit more complicated. So, so as I said, I just wanted to give you a flavor, just a flavor of how things are, how infrared divergence are in gauge theories, because this is a complicated subject. Various famous people have spent their lives trying to define this infrared divergence and factorization properties correctly. So I'm just giving you a simple treatment. So I think that was everything I wanted to tell you today. Do you have questions? All right, just somebody check that you can still hear me. All right, good. So if you can still hear me, that means probably you don't have questions. So I'll see you next Tuesday at 10. So next Tuesday is normal at 10. All right, bye.